Welcome, everybody. My name is Larry Kaufman. I'm the Executive Director of the Michigan Geothermal Energy Association. I'd like to welcome you to the Advanced Heat Pump Seminar. For this seminar, you should be somewhat familiar with the operation of a heat pump. If you are not familiar with the operation of a heat pump, you're probably better in track one. However, if you are familiar with a heat pump and you want the advanced and the technical and the real nitty-gritty and the finer details, you are in the perfect place, and we have the perfect seminar for you. We have two experts on the subject. I'll stop talking so they can talk because they have more to say than I do. Our first is John Semmelhack. He's the owner of Think Little. He's also the co-owner of Moderator Comfort Solutions, home performance consulting and contracting based in Charlottesville and Richmond, Virginia. And they specialize in building enclosure and mechanical systems. And John will speak 20 minutes, Rob will speak 20 minutes, and we'll leave 5 minutes for questions at the end. So take it away, John.
Thank you, Larry. Okay, here we go. So I'm John Semmelhack. I'm with Think Little and Moderator Comfort Solutions. We are home performance consultants and contractors. We're based in Central Virginia, but I got the invite from Brett Little to come remotely speak at this conference, which is great. We do a ton of work with high performance houses and high performance retrofits with Airsource heat pumps. And so that's what we're going to be talking about today. This presentation is really geared especially towards, more advanced clients and geared towards HVAC contractors, engineers who may be thinking about using heat pumps in Michigan. We'll mostly be talking about single split heat pumps, mostly residential, and let's go from there. So just a little background on me. I'm from the Chicago suburbs, so even though I'm in Virginia, I know the cold a little bit, and I've spent a good bit of time in Michigan visiting cousins and aunts and uncles in the Grand Rapids area, and my mom and stepdad now live in South Haven, so we make it up to Michigan a good bit. So it's a place I really like to visit. So why are we talking about heat pumps? This is part of the big picture here that Dr. Brown was just walking us through. In order to get to a net zero carbon economy by 2050, a big part of that has to happen through clean electricity, zero carbon electricity, and electrifying everything that can be done. And residential heating and residential water heating and other space heating is definitely feasible, and it's just not that difficult to do. And we have the tools to do that right now. So in Michigan, as Dr. Brown mentioned, you've got now a goal of a net carbon zero economy by 2050, and your two biggest electrical utilities, Consumers Energy and DTE, have goals for net zero electricity by 2040 and 2050. The other thing about heat pumps is that, especially with variable speed heat pumps, they're also just better suited than a lot of furnaces to providing comfort in home. So the variable speed heat pumps that I'm especially going to be talking about are better able to match the heating and cooling loads, ramp up and ramp down as needed, and provide just exceptional comfort. And we really find, even in cold climates, that customers are happier with variable speed heat pumps than with fossil fuel furnaces. Okay, moving on. So let's talk about climate briefly. Michigan is one of the very few states that's not mountainous, but has 3 different climate zones. Climate zones 5, 6, and 7. Most of the population in Michigan is in climate zone 5. And you can see, so your design temperatures, 99% winter design temperature. So this is in an average year, 99% of the hours of the year are going to be warmer than this temperature. So for most of the state, that's like in the high single digits. And 50-year lows, this is pulled from the ASHRAE climate tables. I'm seeing 50-year lows around -20, a little bit colder in a couple of spots. Just for comparison, where I am in Charlottesville, Virginia, our design temperature is 19 and our 50-year low is -4. But we do get pretty cold in some of our mountain spots in Virginia. Hot Springs is 7 degrees and -21. And then for the folks in the UP who are in climate zone 7, you've got some real extremes where heat pumps are more challenging, but not impossible, where you've got -8-degree design temperatures and -35 50-year lows. Okay, so as many of you who work in Michigan probably already know, heat pumps are not popular currently in Michigan. The default is really gas furnaces in existing homes and probably still in new construction. And so I just want to tell you a little bit about the numbers in terms of heat pumps and tell you a story about Sweden. So in Michigan in 2009, you had about 1.5% of the households in Michigan had heat pumps, but that's growing very fast. In 2015, just 6 years later, that already doubled to 3%. Sweden, which has almost exactly the same population and climate zones to Michigan, was in the same boat as Michigan back in the 80s and early 90s. And now, whereas Michigan has maybe 100,000 households with heat pumps, Sweden has millions of heat pumps installed. As of last year, about 2 million heat pumps installed for 10 million people. It's a $1 billion per year industry. 50% of single family homes in Sweden have at least one heat pump. It's become the default for new construction. And that's something that could happen in Michigan going forward. So this is something, in order to hit that 2050 goal and the interim targets, Michigan's really going to have to super ramp up heat pump installations, and that also means big business opportunities and job growth as well, which is great. Okay, let's talk about heat pumps more specifically. There's a great resource for cold climate heat pumps.
Testing.
And that is the NEAP, that's the Northeast Energy Efficiency Partnership, cold climate Airsource heat pump database. So most of the major manufacturers that sell heat pumps in the US have at least one cold climate model that meets these specs. It has a variable speed compressor with at least 3 speeds or fully variable speed, has a heating season performance factor of at least 9 or heating factor of 10 for ductless systems, and has a coefficient of performance in heating mode at 5 degrees of at least 1.75 at max speed, and it has a SEER 15 or higher for cooling. This is a great resource to go to explore some of the details. One of the great parts, what's really important about here is that it's a great place to go for details on the cold weather performance for these heat pumps. So all of the manufacturers who publish information in this database are required to publish the maximum heat output at 5 degrees outdoor temperature, which is really close to a lot of your design temperatures, which is great. So as you start getting into the details on heat pumps and various models and what's their heating output, you're really going to want to dig into the details in the expanded engineering tables or engineering design manuals. Each manufacturer has their own lingo for what they call this, but this is kind of what it looks like. It's a table or a graph that shows outdoor temperatures and indoor temperatures and heating capacity or heating output and power input, so you can calculate COP. This is for a particular manufacturer's nominal 2-ton or 24,000 BTU per hour model that can put out 18,000 BTUs per hour at -5 degrees. One of the big questions that you'll get into as you start to explore heat pumps for your clients is how cold can it be outside with heat pumps still working? There's of course a common misconception that heat pumps stop working at freezing at 30 degrees or 32 degrees. And that's just not true. And they do keep working. And the more advanced cold climate heat pumps speed up their compressor speed to continue with substantial heat output, even at very cold temperatures. So each manufacturer is a little bit different. Some manufacturers publish their actual cutoff temperature, where the outdoor unit will actually shut down and the air handler keeps going. And then other manufacturers don't actually publish that, so it does vary. So as you do your heat load calculations, you'll need to consider, do you need supplemental electric resistance heat? In some cases with really high performance houses, you might not really need it. And then you get into a conversation with your clients about, what do they want to do for backup? Do they want to have electric resistance backup heat that's integrated into the air handler? Some clients just prefer to have an electric fireplace, or they put a couple of electric space heaters in a closet and pull them out if there is a mechanical problem with their heat pump ever. This particular heat pump that's in the picture, this is installed in Minnesota in a 100-year-old house that's gone through a couple of very deep super insulation retrofits, but it's a 1.5 ton nominal heat pump. This model, to everyone's knowledge, has no known lower limit. During the polar vortex a couple of years ago, it was still running at minus 28 degrees Fahrenheit on January 30th in 2019. It wasn't designed to heat the whole house at that temperature, but it did keep a 3,000 square foot house above 50 degrees on those couple of polar vortex days without any supplemental heat while the owners of that house were away on vacation. So that's really cool. Getting into the details of designing with these systems, you'll want to, really dig into the typical hourly temperature bins from your heating and cooling load calculation software or other sources. This is for Southwest Michigan from the software that I use. In a typical year, you're going to find in most Michigan locations, you have fewer than 100 hours with temperatures below 10 degrees. So even if you do need some electric resistance supplemental heat for your heat pump system, it's not a big overall energy or energy cost penalty to pay. Okay, moving on. Especially in heating dominated climates like Michigan, there's a tendency to oversize heat pump systems because in most houses, the total or peak heating demand is greater than the cooling demand. And naturally, you want to cover it with a more efficient heat pump than rather than relying on electric resistance heat too much. However, an issue with all of the variable speed equipment is that if you oversize too much, the systems during a lot of the year can start short cycling, where the minimum output of these systems is greater than the actual load on the building. And the systems actually have to turn off, and then they turn back on, and then they turn off and they turn on to meet the load. And lab testing from the National Renewable Energy Lab shows that when these kinds of systems are operating in this kind of on and off manner, their efficiency drops by 20 to 40%. So it's still best, in my opinion, to follow traditional sizing rules using ACA Manual S in most cases, which when you're using variable speed heat pumps, call for sizing systems so that the cooling capacity is no more than 160% of the cooling load. And then you look at your heating capacity and add supplemental heat as needed. Our experience here in Virginia, as you can see from the slides, is mostly with the side discharge models that are popular with the Asian manufacturers. Most of the North American manufacturers, even in their cold climate heat pumps, are using vertical discharge. But I wanted to offer a couple of slides, especially related to the side discharge models in terms of installations for cold climates. So this installation is here in Virginia. This was just done, installed on a concrete pad. And you can see at the bottom of this outdoor unit, you're getting some snow buildup, and you're starting to get some frost creeping up the back of the outdoor heat exchange coil. And that can be a real problem. So in cold climates with a lot of snow load, you really need to raise these off the ground. Something like this kind of stand that gets them off the ground about a foot. This is that Minneapolis location. The owner has actually gone back and raised this heat pump up even further. And the reason for that is that during defrost mode, they were getting refreeze off of their defrost melt. So you can see the defrost melt here, refreezing on the ground and then starting to creep back up. This particular model does not have a drain pan heater. Some models do. So that's going to be something that you should look at when you are selecting equipment, whether or not a drain pan heater is needed, whether it's an optional extra for your particular system. And what kind of safety attributes you're looking at, because you don't want your defrost to start creeping up the backside of that heat exchanger. That was a little video. I don't know if you could hear it or not, but there was a loud clickety-clackety, clickety-clackety sound because the outdoor unit fan blades were contacting ice that had built up on the outdoor frame. And this was an interesting case. This happens once every few years around here, where we get snow and then it's still cold but sunny. And so the sun melts the snow that's on top of the outdoor unit, and that snow melts and starts dripping down over the face, the front and the back of the outdoor unit. And if it's cold enough, it will start refreezing. And so that's what happened here. That snow melt was refreezing and then building up on the fan opening. And so what we're doing going forward is when we install these, we're just pitching them very, very slightly to the rear so that any melt will drain off the back. And when the unit goes into defrost mode, if there's any kind of refreeze that happens on the coil, the system can melt that snow when it goes into defrost mode.
2 minutes.
Other tips on these side discharge models, make sure you don't do this where one unit, if you have multiple units like in this townhouse scenario, one unit is kind of blowing into the back of the other. Definitely try to avoid that. With ductless units, which are popular, especially for additions or particular rooms, ductless units really need an annual cleaning. This is the blower wheel on the inside of a ductless unit after just 1 year. Many of you who do these cleanings have probably seen much worse. We definitely strongly recommend cleaning every year for these units. And then going into some data for you. This was a new construction house that we worked on here in Central Virginia. This particular heat pump this was several years ago, but we had a quite cold day for us. We had an 8-degree outdoor temperature low, and the energy used for that heat pump for about a 2,000 square foot house was just over 20 kilowatt hours for the entire day, which is about $2.50 to operate that heating system for the day. So we think that is quite good and pretty comparable, maybe even better than what you would see with a high efficiency gas furnace and really, really cheap gas prices. And finally, I want you to remember that, especially for retrofits, these are opportunities to do additional work on the enclosures, improving the air tightness, adding insulation where it makes sense. And that can also help, especially with the older, leakier, poorly insulated houses, bring their heat loads down low enough where a heat pump can really make sense. So thank you for your attention.
Thank you, John. That was terrific. We really appreciate that. Our next speaker is Rob Dirksen. He is the owner of Michigan Energy Services. They are one of the largest geothermal dealers in Michigan. And for full disclosure, I should mention that when I started my career, basically Rob Dirksen, Jim Norrod, and Jerry Getz taught me the energy efficiency in geothermal. Basically everything I know I learned from them. So I mean, absolute gratitude for them for teaching me this industry, and done lots of seminars with Rob. Is one of the best speakers you'll find, and here to tell us about geothermal heat pumps, Rob Dirksen.
Thank you, Larry. I appreciate that very much. I'm going to be talking about geothermal heat pumps, heating, cooling, and hot water, and how they apply to net zero homes. A little background on me. I'm celebrating the 30th year in the industry and 22 years as a geothermal contractor. So I'm coming to you today from a perspective of having worn each hat in this industry, from shipping products to installing products to actually digging the trenches, applying the loop systems to the geothermal equipment in the homes. So start to finish, we've been involved in everything. John made a really interesting point about the Swedish movement towards electrification. Just a point of interest here is the top 3 geothermal manufacturers in the United States are now owned by a Swedish company, and they're owned by the same Swedish company. So if that's an indication of where the Swedes think that the US market is going to go with electrification, I think that's a good indicator that we're moving in the right direction. So with no further ado here, we'll talk about geothermal heating, cooling, and hot water, and how it applies to net zero homes. The first item on the list here is geothermal offers the lowest electrical consumption of all of the electrical space conditioning systems. John mentioned COPs and EER values. The geothermal equipment has COPs approaching 4 and 5, with EER levels at 30 plus. And these are not, they're not regulated by outdoor air temperature, because our geothermal systems are obviously pulling heat energy from the earth, which is a stable, constant temperature. So that provides that additional level of capacity and the additional level of efficiency. Because all the equipment is located in the home, we also enjoy the lowest maintenance costs available to any heating and cooling system. Geothermal equipment is not subject to outdoor environmental conditions. If you happen to be in a coastal climate, your life expectancy on an outdoor air conditioner can be as short as 7 years based on salt air and other environmental conditions. And so we have a longer life cycle cost. And then we have a centralized system, which allows us to enhance our indoor air quality. So where the opportunity may seem favorable to look at a split or a mini split system without a centralized duct system, there are some considerations that you want to take in how are we going to handle the indoor air quality for our occupants. So here's some considerations that I want to talk about in designing a geothermal heating and cooling system for a home. First on the list for net zero is occupant expectations and tolerances. Having been involved in several net zero projects, one thing that we have learned about our occupants is that not everybody wants or needs to be at 72 degrees, 24 hours a day, 7 days a week. There is a level of accepted range of temperatures. And so it's important for us in the design process to talk to the customer, talk about their expectations, talk about where they want the home temperature to be preferably, but then also understand that if temperatures vary from that desired set point, what will their tolerance be? That always factors into the controls. Geothermal can control heating and cooling temperatures as tight as tenths of degrees. We can literally maintain a 0 differential in a home at the thermostat. If it's set at 72, we can maintain precisely 72 degrees. But that comes at a cost. That comes at a cost of energy consumption. And if we're trying to achieve a net zero, we want to minimize consumption whenever possible. We also want to take a look at any alternative free energy sources and how those will impact our design. And as a building community, as a net zero community, we're learning more about alternatives, a good passive solar design, active solar, being solar thermal, as well as trom walls and how they impact the heating load of a building. Quick example, we did a net zero home, which also received the Living Building Challenge certification here in Ann Arbor. And their trom wall system in certain days of the winter will actually provide enough energy in the home where the occupants are needing to ventilate and get rid of some additional heat. The home heats up beyond 75, 80 degrees just through the passive part of their system. And so we need to take that into consideration when we're designing and sizing the geothermal equipment. We also have to understand the true load characteristics of the structure. John alluded to the proper heat loss and gain calculations. That's a must, and that'll impact the system sizing and can do so dramatically. We need to understand the data. We need to talk about the kilowatt hour consumption projections. And then obviously we'll also talk about proper loop design and how that impacts the operation of the system. So doing proper load calculations, we really need to use a good load calculation software to fully understand where our load is being driven by. Are we losing our energy through walls or infiltration or windows and ceilings? And we need to find our maximum levels of efficiency in those areas. There are times where people will put 20, 30 inches of insulation in the attic, but then they may ignore the lower level foundation walls, and that's a larger heat loss. So there's always a point of diminishing returns. And if you partner with a good heating and cooling contractor that understands how to do a load calculation, or they partner with an energy modeling company that can help you put all the parts of the puzzle together, that can really improve the system sizing and overall upfront cost. When we're sizing for the actual house load, one of the benefits of the geothermal industry is that most manufacturers for years have been using software that models energy consumption. We have been talking about the message of efficiency and low energy costs for decades, since the late 70s, early 80s, when geothermal became a viable product and came onto the residential scene. This is just an example showing that in the heating mode for this particular plan, we're going to use around 3,400 kilowatt hours seasonally for heating. We're going to use about 1,060 kilowatt hours for cooling or for hot water generation, and then about 500 kilowatt hours for the cooling. The important part about this is that when we're trying to model this net zero home, the most important factor is to try to determine the amount of kilowatt hours we need our solar array to produce. And so we don't want to guess at this figure. So using an energy software that will model the kilowatt hour consumption is extremely important in our design process and early on in the discussion phases of the project. The bin data, again, is the same kind of information shown with the Airsource heat pumps, as we can understand our equipment's operation at the various outdoor temperatures, how many hours we're going to operate, and then how many kilowatt hours we estimate to be consumed in that bin of weather. We have a system here that would begin to use some auxiliary heat around 7 degrees above zero, and that would be considered a normal application here in the north, especially in Michigan. We'd like to have what we call a balance point of somewhere around 10 degrees or colder before we would expect or accept the use of auxiliary heat. Now, geothermal can be sized to 100% of the load, and the most extreme temperature that the state of Michigan or any state in the country really could throw at us. But it's not economical to do that. The cost of oversizing a system and the additional piping needed to put into the ground loop would far offset any consumption savings in power. You could see in this center column, the auxiliary heat in this application is 121 kilowatt hours per year. That at the going rate of electricity is somewhere around $15 worth of energy. So to increase the equipment size and increase the ducting size and increase the geothermal loop size would provide no value in reasonable recovery in energy cost or energy production for that matter. So utilizing software that provides us with kilowatt hour estimates based on the weather for the area is very important. We can also further break down that data to kilowatt hours per month based on historical weather data. And if you wanted to break that down even further by day, we can use this modeling to match the design of the solar array to try to get as much energy produced from the solar. Becomes especially important if we're looking at adding battery backup systems and understanding how long those battery backups will last for running the geothermal system and other base loads of the structure. So breaking down all the detail and the data is extremely important if you want to have a successful application. Correctly sizing the loops are imperative to successful geothermal applications. We do expect the minimum entering loop temperatures here in Michigan to come in around 28 to 30 degrees in the wintertime, and that's fine. That's considered a proper design. Whether or not you're using a horizontal or a vertical loop, they will perform at the same efficiency level. The only thing that changes between horizontal and vertical loops for the client is the vertical loop is a more expensive installation, but it can go in a much smaller area. So we're not limited to large rural properties. We can take geothermal systems right into the middle of the city. A typical home, we can install a vertical loop in a 10 by 10 area in the front yard or under a driveway. We have a lot of flexibility in where these systems can be installed. We've done them in downtown Ann Arbor where the drill rig is actually located on the street. We have to shut the street down while we're going through the drilling process. So we've been in some very tight applications. Northern loop installations in places like here in Michigan will always be dominated by the heating requirement of the building. And so there's always excess energy available in the summertime from that loop system. I've shortened my presentation up here considerably today, so we'd have times for questions and answers. Here's my contact information that you're welcome to write down and record and contact me either at my cell or either the emails there. We have all of the modeling software needed to help you with your project and go through very detailed analysis to meet whatever objective that you're trying to accomplish. And with that, Larry, I'm going to turn it back to you and see if we have some questions and answers we can go through.
Oh, okay, thank you. So before we start, send me questions and I will pass them either to John or Rob. They're both still here, both still awake. Maybe you should start while we're waiting for questions, Rob. We used to talk about in the seminars your own house, which you built, I believe. And maybe you can give some of the heating and cooling and heating, cooling, and water heating numbers for your own house, some of the details.
Yeah, I built my house, Larry, back in 2000, back at kind of the early days of the Energy Star program. Just a quick background, the house is a 2,800 square foot ranch on a full walkout basement. I have about 18% glazing, so I've got a lot of glass facing predominantly northeast is my glazing direction. My energy consumption for my house averages somewhere around $80 a month prior to my installation of solar.
So basically you have 5,600 square feet of space that you're heating, and you have $80 a month in bills for heating, cooling, and water heating. When we used to talk to people in Detroit who had 1,500 square foot homes, they had higher bills than that. So that shows you what can be done. So again, if you have questions, send me a question. Maybe we'll have both of you on. We're waiting for questions. Can we address when should you use an air source and when should you use a ground source? Or is that purely whim of the customer or financial? I think that's a really interesting question.
Yeah, that is a good question, Larry. I'll go first, and then I'll give John a chance to respond too. It's really not about what we think is right for the customer. It's about understanding the customer's wants, needs, and goals, and how the different products that are available today answer, and help them achieve their wants and their needs and their goals. So if budget is no concern and you want the highest efficiency system possible with the longest life, geothermal's, the ticket. If you want to, save a little money up front and you're okay with a little higher consumption, an air source is a good choice as well. Anything that's electric is better than a fuel. Let's put it that way.
John, your comments?
Yeah, I think certainly the air source heat pumps are going to be lower upfront cost, and compared to the best installed geothermal systems are going to be higher operating cost for the air source heat pumps. So yeah, it definitely depends on the client's goals, their budget. One of the things that I like to think about as well is that there's fewer things that can go wrong with an air source heat pump. It's a little bit more of a known entity. Each geothermal heat pump installation requires kind of a custom designed heat exchanger in the ground. When that's done well, they're fantastic, but they're not always done well. And so that can be the danger there with the geothermal heat pumps.
So I have a question from Wayne AP, but I'm betting that's Wayne Appleyard. Hopefully, maybe I'm correct, maybe I'm not. And he asked for a cost comparison between air source and geothermal. Now, I just want to comment. To me, when people say I can't afford geothermal or I can't afford a heat pump, I always answer you can't afford not to have one because you're going to pay more in utility costs over the year. And whether it's an air source or a ground source, it's going to pay for itself. But to answer Wayne's question, maybe you can address the cost comparisons between an air source and a ground source. And again, I know ground source can be open loop, vertical, or horizontal, so there's some variables.
Yeah, that's a good. The variable is all over the map. But suffice it to say that when we look at components and we look at a geothermal system as a package system, typically in a basement, it has the compressor, the air coil, the fan, the heat exchanger for the loop system, all built into that system. Air source, we have components, they're just in separate places, right? We have our outdoor portion, we have our indoor coil, we have an air handler. So we really have all the same components. And similarly, those costs are very compatible with one another because we're not talking about any distribution changes in the house. Ductwork is ductwork. So really the difference comes into the installation of that ground loop system. Our heat source for geothermal, we need to get that in the ground. And so with those variables on say an average 3 or 4 ton home, you could be spending anywhere from say $6,000 to $12,000 on a loop system to support the equipment. So in this case, that's about where our differential would be between a high-end air source heat pump application to a geothermal. Most of that difference in cost is going to come from the loop itself.
Yeah, and I think I'd just like to add, just in terms of cost in general, the best time to install a heat pump is when you need to change out your heating and cooling system anyway. So you're really just talking about the kind of marginal cost difference between, you know, a business as usual gas furnace and AC swap out versus switching over to a heat pump. So if you just installed a furnace, you know, last year, okay, you know, maybe if you've got a lot of money, go ahead and switch to a heat pump. But otherwise, wait until it's time. You know, most systems, most air conditioners and heat pumps, average lifespan is about 15 years. Wait until it's, you know, gone through its life cycle, and then plan for a swap out to really minimize any difference in upfront costs. I think you're on mute, Larry. Yep.
No, it's not. The host is doing it. So I also want to address, it's not just cost. We sometimes look at it strictly as cost, dollars and cents, but there's a lot of environmental benefits. A lot of people here, if we want to protect the environment, we talk about climate change, we talk about carbon footprint. There's a lot of environmental safety issues. The fact that there's no gas, which can cause you know, explosions or carbon dioxide or all kinds of other things. So there's a lot of other reasons other than strictly cost alone. Sometimes we tend to look at it, well, X amount of cost versus X, but there's so many other benefits, and people buy for various reasons. Some people buy strictly in cost. Other people will buy for the environmental. I mean, you know, or they want to do what they can do to work. I got a couple other questions. One I'll address, and then I want you guys to address. The one person asked about what is this performance of a heat pump, and I can say when I worked for DTE, we did customer satisfaction ratings, and the customer satisfaction ratings of our heat pump over hundreds of responses was in the 90+% versus 70% more or less for a conventional system. Most people rate the conventional system as average. Most people rate their geothermal system is either very good or excellent. It's kind of right in between both. So the performance of a geothermal system was much, much higher than conventional. I got questions, two questions. You can address them, whoever wants. One is on tankless water heating. One is on just water heating in general. And the third one is on the cost of an open loop versus a closed loop. So you guys fight among yourselves, see who wants to answer.
Rob, why don't you talk about the open loop, closed loop first, since that's directly related?
So open loop is where we're pumping groundwater and then we're discharging that water after we've run it through the heat exchanger of the geothermal equipment, where we're extracting, you know, 5 to 10 degrees in heat or rejecting 5 to 10 degrees. Open loops are the lowest upfront cost because you don't have all the infrastructure to put in the closed loop system that recirculates the antifreeze system. The downside of an open loop is that in Michigan, in most states, you're subject to whatever your water quality is, whatever's in your well water in terms of mineral content, iron bacteria, hardness, salts, and so that can lead to
about 1 minute. I think we only have about 1 minute or less. So okay. John, if you want to address water heating, and for anyone else, hopefully you'll stay with us for the networking at 8 o'clock, and we can answer more questions, and hopefully our guests will be there for that. But 1 minute, and I got to turn it over to you.
I mean, in terms of water heating, I'm a big fan of heat pump water heaters. If you stay on this track for the next session, that's on high performance ventilation and heat pump water heaters. So the next one has a great product from Rheem that I think they're going to be talking about, that technology that I'm a big fan of. It makes a lot of sense, especially for homes with basements.
I think we're out of time. I'm not sure, but I want to thank John and Rob. You guys did a great job. I think people should have got some really good information. I want to turn it over to my partner in crime, David Dye. I've spent the last 6 months every 2 weeks on a phone call, and he's been an absolute pleasure to work with, and I'm sure he's going to do a great job for you.